Hey, it's day 82, and we're going to take a look at Stoich and titrations, as well as what these things called buffers are and how they work. The magical 7 steps to figure out the molarity of an unknown acid using titration. I know. Yeah. Now, key things, of course, is you should be able to solve problems like this. I got some aluminum hydroxide, I got some nitric acid, just about pH and stuff like that. The next one, of course, is I want to know what buffers are, and you should be able to give examples of at least one, or maybe a couple of these, right? So, pause me, write down the question, and then we'll take it on together, right? Cool. Let's get rid of my big ugly head. Woo, there it goes. Cool. If we look at this first one, any time that we have a problem, the first thing we want to do is figure out what we got and what we need. And we can see right here that it wants to know how many grams of aluminum hydroxide. Well, that's crucial. That means that at the end of this, I should have grams of aluminum hydroxide. Next thing I notice is, hey, that's a hydroxide. That's a base. So if I want to know what a base, that means that I probably want to figure out and start with my acid. Now, the other things that I have in here is I've got 252 liters of an acid called nitric acid solution, and it tells me the power of its hydrogen, its pH, is 3.5. So if I'm going to solve this thing, I'm probably going to want to start with my acid, but that means some crucial things. I'm going to need to know what the reaction looks like. So first thing I'm going to do is I'm going to write a balanced reaction. I'm going to start by tradition and write the acid first. There's my nitric acid, and it would be aqueous if I wanted it to do anything fun, right? And then if I'm going to react that with my base, that's the aluminum hydroxide, because they're giving that away for free, and that is also aqueous in this case, right? Because there's solutions that we're going to do a titration, which is what this is. And, well, I got two solutions. What could they do? The old switcheroo, right? And when they do the switcheroo, it's an acid-base reaction, so I can make two things. I can make salt, and I can make water, right? The salt that I could make means that the cations would exchange over here, and I get some aluminum nitrate, right? And when I do that, of course, it's 3 plus and a 3 minus, so they come out nice and neutral, neutralize your compounds. That's going to be aqueous because it's going to happen in a solution. And then, of course, I'm going to have, what's the other thing coming out? Some water, and it's brand new water, so that's the liquid kind, right? It'll quickly mix with the aluminum nitrate, make a solution, but it's brand new water at this point. Then, of course, I always got a formula. I got to make sure it's balanced. And I can see right here that I got an issue because there are 3 of these hydroxides, and that's changing over here. So that's a pretty good. So I'm going to need 3 of those hydrogens. So there's going to be 3 of those nitrics coming into it, and that's going to make me 3 waters, and then boom, everything's balanced, right? Now, cool things about this, I want to know something about my base. So I'm going to start with my acid. That's usually the trick of this thing. I don't know anything about the number of moles there, but I do know its pH, and that's great because I can use that to find the hydrogen ion concentration, right? Now, what I do there, of course, is I don't need to use a log because I got a P, so all I do is use my P as a power. I take the negative pH and use that as the power to actually go in and amplify the 10, right? When I look at that, of course, that's going to give me the concentration of the nitric acid because that's what's supplying the hydrogens. And then I would just take 10 to the negative 3.5, right? When I punch that in the calculator, it does the heavy lifting. I'm going to cheat and use the 2 siggy figgies. It's 3.2 times 10 to the negative 4. And that, of course, is the molarity of the nitric because that's what's giving you those hydrogens. It's the hydrogen part of it that we care about. And okay, well, that's something I can start with because that means I can start with my acid, my 3.2 times 10 to the negative 4, and that's molarity. So that's moles over 1 liter of nitric, because you should always split that up and make it moles per liter for the big M. And then I can stoich my way to get to my base, right? All about that base. When I do that, I should recognize I don't have 1 liter of nitric. I have a lot more. I have 252 liters. So I'm going to stick that on top because in my one sample, liters and liters will cancel, and that'll show me how many piles of nitric I have. Now I want to get to my base, so hey, that's where the stoich comes in. I'm going to use my mole to mole ratio, and when I do that, I'm going to get rid of my acid, my protons provider, and I'm going to turn it into my base, my aluminum hydroxide. Now, the cool thing is you got your balanced equation up above, and it tells you for every 3 of those, there's 1 of those, right? And you can also just look right here. There's 1 H for every, there's 3 OHs for each of those. So that means I'm going to need 3 times as much of it to make 3 waters. It's HOH, right? Titrations, HOH. Last step, I can recognize that I just killed off moles of nitric. Now I need to get rid of these moles of aluminum hydroxide and turn them into grams, a G thing, right, of the aluminum hydroxide. That's easy. I just use my molar mass. 1 mole of this aluminum hydroxide stuff would have a mass, if you added up the molar mass on the periodic table, your good old friend, it would be 78.03 grams of the aluminum hydroxide. Moles of base go away, and now I'm stuck with grams of aluminum hydroxide, the unit and substance that I need. I punch it into my calculator, and I get exactly 2 sticky figgies, because that's what I started with, because we're taking it easy on us for sticky figgies, and it's 2.1 grams of aluminum hydroxide, right? Now, before I move on, I should recognize, does that number make sense? Well, take a look at this. 2.1 grams of aluminum hydroxide. It's a decent little pile of aluminum hydroxide, right? And it's not that big, especially when you consider that the molar mass is 78.03. I mean, it's a fairly little heavy pile, right? But, well, one of the things I recognize about this is I did have 3 hydroxides in every one of those. So that's going to supply me, a powerful punch of the hydroxides. And I'm going to need a fair number of those things because I got 252 liters of my nitric, right? And my nitric, of course, has a pH of 3.5. So there's quite a few hydrogens that are in there. But the good news is that would be a gram. So this would be a solid pile of that stuff. So it's going to be highly concentrated until I throw it into the solution, right? Awesome. That was easy. Always remember that when you're trying to solve something, balance your equation first. Ask yourself what you got and what you need. I start with what I need first. If it asks about the base, then you probably want to start with your acid. And a great way to find out about the acid, of course, would be to take the pH, because you can do that with an electronic sensor, right? Awesome. Now, what are buffers? And can you give examples of it? At least one. Well, think about the name, right? They're called buffers. Does this mean the buff? Then keep your builds? What kind of? You need a buffer anytime you work out because you feel that burn, right? So let's get some notes on that. Buffers basically buffer the pH change. They resist changes in the pH and keep it stable. They buffer it. Now, if we look at this, of course, it's going to be a mixture of a weak acid and its conjugate base, which means we need a lousy quarterback like vinegar and its conjugate base. And if it's a weak acid, it's going to be a strong conjugate base. And acetate is a strong conjugate base. It's a great receiver. So what this does is it prevents big changes in the pH and stabilizes the pH, because acetic acid, of course, is a weak quarterback. And being a weak quarterback, it doesn't really like to throw the ball, right? And the neat thing about it is if we look at the structure of it, one of the things that we'll find out is it's got, of course, attached to it this lovely thing called a carboxyl group. And what it has on it is an oxygen, and then it has this cool thing called the hydroxyl group, right? And as we look at this, this is the proton football that gets thrown. This is the proton that gets out and throws out there and burns things, right? When you eat vinegar chips or something like that, stings in your mouth. The neat thing about it is as soon as it does that, this other oxygen here is hogging the electrons, and it quickly grabs onto that proton right away and acts as, well, the acetate ion, which is now a strong conjugate base. So as soon as it throws the football, it grabs back onto it. And that helps to keep the pH from shifting too much, because it means that the protons that go into solution quickly get gobbled up. So anytime you have a combination of, a weak acid, a really bad quarterback, and its strong conjugate base, any proton that gets thrown is going to get gobbled up, so the pH is going to stay fairly stable. Now, why is this important? Let's say if you went to Tokyo and you wanted to have a whale shark in your fish tank. Its job is to gobble up the extra protons and donate protons if they're needed, basically keeping it at equilibrium. You'll notice that this is a make it or break it reaction. It can both be destroyed or come back together and form. Hey, it's almost like equilibrium is what acid-base reactions are about, throwing proton footballs and then picking them back up, receiving them. So if we look at this is important for giant aquariums or little aquariums, anything that has a solution, because of course there's a lot of water in there. And of course, you're made of water. So this is how you keep your blood pH from dropping too low. And anytime you worked out, felt that burn, you're experiencing where the pH is shifting, right? Good thing you got buffers. So this is why anytime you have an aquarium or a swimming pool or something like a hot tub, you're often adding buffers, which would be weak acids and their conjugate bases. Kind of keeps the pH from getting too far off, especially if somebody's peeing in the pool. And all these fish, of course, would be releasing ammonia, which would change the pH of the pool. It would make it, of course, go up. So you need to buffer those changes. Best example of this by far, we hit in AP Bio all the time, but hey, it's not like chemistry has anything to do with real life. It's just real life. And if we look at this, the buffer that we use in real life is this stuff called carbonic acid and its conjugate base, bicarbonate ions. Now, the cool thing is, of course, we've already figured out that when you take a weak acid like carbonic acid, it will dissociate and it'll throw out protons because it's an acid, right? It's proton football. This is a lousy quarterback, and this is its strong conjugate base. So as soon as it throws out the proton, this carboxyl group, which is what the carbonate's made of, has inside of it, it actually takes and it gobbles that back up. And when it does that, hey, you're catching every proton that gets thrown out, right? Now, the key thing of this is it's going to donate protons if your pH gets too high. It's going to gobble up protons if it gets too low. And that means that your pH stays stable. Now, key things about this, of course, is when you work out and stuff, you start to build up things like lactic acid, as well as you're chopping hydrogen ions off of sugar, and that builds up concentration gradients in your outer part of your mitochondria that have a lot of protons, and you start to feel that burn as you become acidic. Your pH is dropping. So the good news is your body uses this bicarbonate and the carbonic acid to gobble up any protons. And of course, hemoglobin has another factor in that, which we'll learn in an AP Bio video, but that's out there too, right? Now, key things about this, of course, if the pH gets too low, that would cause all of these blood cells to change shape in their proteins. They would denature, and then they wouldn't function anymore. But that's the beauty of hemoglobin, as well as bicarbonate ions and weak acid to buffer the pH changes, keeping you alive, right? Now, if we look at the other part of this, you also affect your pH just the same way that the ocean does. You breathe out the CO2 when it starts to burn too much. You've been running, and you start huffing and puffing to get the CO2 out, because it's the CO2 that becomes the carbonic acid that burns you. Now, unfortunately, of course, this buffer that buffers our body, we stole from the ocean because our ancestors were fish. And if we look at this, of course, this is exactly what's causing ocean acidification and also preventing ocean acidification to becoming as bad as it could be. So it's kind of a neat process. As the CO2 goes in, as we talked about before, it bumps into the water, makes carbonic acid. The carbonic acid is a weak acid. It dissociates and makes hydrogen ions as well as bicarbonate ions. Now, the cool thing about this is that means that the ocean would have inside of it its very own buffers, the weak acid and its conjugate base. Now, what that means is it'll gobble up the protons if there's too many, and right now there's too many in the ocean, and that prevents the pH from shifting as much as it would if, say, you had a strong acid being dumped into the ocean. Thank goodness CO2 does not make that. Now, as that does that, of course, one thing that we'll notice is it also can dissociate and make carbonate ions. If carbonate ions are in the ocean, which they have naturally been, then the hydrogen ions that are produced will be gobbled up to make more buffer. It's just a matter of collisions. It's going to collide with them more often. Unfortunately, that's what the ocean is doing, and the place that it gets the carbonate ions is from the solution. Most of those are eaten up quickly because there's not a lot of that in the ocean free and moving around. So then it steals it from shelled creatures. The calcium carbonate that's there, it's the carbonate ions that are stolen by the protons in their overabundance to make a buffer to buffer the ocean. So the neat thing is, through equilibrium and Le Chatelier's principle, this buffer reaction is basically causing it to prevent the ocean from becoming as acidic as it could be with all the CO2. But that's why scientists and civilization didn't realize how bad the problem was with all the CO2 creating carbonic acid, making the ocean acidic, because the natural process of Le Chatelier's principle, this is creating stress and causing collisions, is making a buffer to prevent it from dropping as much as it could have. So we were like, it's not changing that much. Well, it would change a lot more if it wasn't eating away at all the coral reefs and marine life that we rely on for food. So all the living things are buffering the pH change because of our combustion. Chemistry has a lot to do with real life. Well, I just said that. Now, key things we would then look at normally is we'd look at Lab 24, where we were titrating an unknown acid to find out its concentration. And when we were doing that, we were mixing it with a base that we know. So that takes 7 steps. This is the curve that it would produce. And you wouldn't do it in one shot. What you'd do it is you'd do it in pH intervals. And you'd march the pH up from the acid land. Here's my analyte. This is the acid, the hydrochloric that we're testing and want to know the pH of. And then I'm adding base to it, sodium hydroxide, of a 0.1 molar concentration. And we walk its pH up in steps, going from acidic land, low pH, to basic land. But what we really care about is how much sodium hydroxide we added before and after the largest pH change. And that's because it's going from an acid land to basic land. And in between there, it was neutral land. So if we started with a 0.1 and you put 10 milliliters of the acid into the flask that's below it, we titrate it down into it. And that would, of course, then give us some jumps. The spot that we typically find would be like 13.28 milliliters. It'd be right in this range here because we got a strong acid and a strong base here, right? It's good proton football. And then the shift where it would jump from there would be to basic land, and that's 13.41. Not a huge difference between them. What we care is we then take the average of those two, divide them by 2, and there is the actual volume that you'd have. That would be the equivalence point where the H's and the OH's match. Then I just use some simple mathematics with dimensional analysis, and I say, okay, I got this many milliliters of that. Well, if I convert that to liters and divide that by, or multiply that times the 0.1 moles per liter, I would find out that I have exactly 0.00133 piles of sodium hydroxide, moles, right? Not a whole lot. Now, key thing is this is NaOH and HCl. That's a 1-to-1 ratio when you write out the formula, and that means that it's that exact number of moles of hydrochloric. And then to find the concentration, all I got to do is take those moles and divide it by the number of liters. And in our case, we would have used just 10 milliliters of it, which is 0.010 liters. So when I divide those moles by those liters, I get 0.133 molar hydrochloric. Hey, look, it's a little bit stronger, and I had to use a little more base than the 10 milliliters, which kind of makes sense because I'm adding in those hydroxides to cancel every hydrogen. The basic idea of titration is a lot like this image here, and I typically do this in class with red and blue bouncy balls. And the red would be the acid, the protons that are in there. This would be a pH that would be lower than 7 because it's acidic. And then in your titration, your burette, you would drop in hydroxides, which are the blues. As you do that, of course, at a magical point called equivalence, the number of red protons and blue hydroxides would equal, and it'd be a pH of 7. But getting that perfect is really hard when we're talking at particles in the millions and millions because it's small land, right? So typically what happens is you drop a little base in, you drop a little base in, and when you do that, you drop a little too much base, a little too many hydroxides, and that's why the solution jumps from acidic land to basic land. And if you take the average, you can find when the pH was 7, which in this case would be a perfect equivalence for hydrochloric acid and sodium hydroxide. Cool. Our target today was to be able to explain how buffers work. Buffers basically are a weak acid and its conjugate base, and their job is to gobble up protons or to release protons to keep the pH stable. If there's more protons in solution, they bump into the conjugate base and they become neutralized. And if they, of course, do that, that prevents you from changing the pH too much because it gobbles up any extra protons that are out there. If we look at the 7 steps for how you find the molarity of an unknown concentration, basically what you got to know is the molarity of the base that you're dropping into your acid. You figure out how much base was put in just before the jump to acid land. You just after the jump to acid land, take the average of those two things. That will then tell you how many milliliters of base that you use. Convert that to liters, turn that into moles of the base because you know it's a known base, and then you use your stoichiometry to convert that into an acid, and then you divide by how many milliliters of acid you have, turning those into liters first, and you get moles per liter. So first, of course, you find out how much base you used to figure out how much acid was in there. Basically, how many OHs to cancel the H's. HOH, titration, HOH.